Hello, everybody. It's time to start. This is our last week. Yeah, it's been a long semester. And now it is time to do more integration. I guess I can ask, what questions do you have? Although that question scares me. I looked at our class has consistently done better than the other classes, the average of the other classes. That's good. You guys are working hard. Wait, shh, quiet guys. You, talking to you. You, Chris, quiet. Shh. Yes. Where was I talking about? I don't know. It's all gone now. Our class is doing better than the other classes. You guys are good. Maybe your TAs are good. I don't know. It's not me, because I don't do anything. All right. Today we're going to talk about substitution. How many of you have seen substitution before? Okay, a lot of you have seen substitution before, and some of you didn't vote. Substitution is not magic. Okay? That's going to be my lesson for today. Substitution is not magic. There is no magic that goes on when you do substitution. Let's talk about what it is. It's the chain rule. It's the chain rule backwards. There we go. That's what substitution is. We call it Lurniak. Okay. So here's the deal. Let's see. I used to be really good at giving this little presentation, but I'm not sure if I'm so good anymore. So if I have f of, I'm going to use g, f of g of x, right? And I want to take its derivative. If I have f of g of x, okay, Bart, pay attention, don't mess this up. And I want to take its derivative. I can say the derivative of this thing with respect to x by the chain rule is f prime of g of x times g prime of x. Great. Now, let's look at two integrals, okay? Would you guys? These things are equal, right? These things are equal. So, so I can write. So I have the integral from a to b of d over dx of f of g of x. This is equal to, because that's equal, it's equal to the integral from a to b of f prime of g of x times g prime of x dx. I'm just integrating both sides of the equation. That's all I'm doing. And I can do that. These things are equal. It means they're the same. Now, you guys know, that when you take the integral undoes the derivative, right? The integral undoes the derivative. And so in particular, this side's super easy, isn't it? This side is f of g of b minus f of g of a. These are equal, right? That's the fundamental theorem of calculus right there. That's the fundamental theorem of calculus. So I have a little string of equal signs here. Now, I know I'm getting super sneaky here, and so just wait for it. I'm going to say this thing here is equal to the integral of f prime, and I'm going to abuse notation f prime of g dg. Oh my God, what's that? G is just some new variable. It's just some new variable with the same name as the function up here, but it's just some different variable. I know I'm abusing notation. I apologize, but there's a reason I'm doing it. And the limits of integration here are g of b to g of a to g of b. And so I could write any letter I want here. You shouldn't write f, okay, or d. But I could use any letter I want there. And it's just indicative. It's trying to indicate that we're plugging in g there. So here's my formula that I'm going to write down. This is the substitution. This is the substitution formula. Substitution. This is a good formula. It will not lead you astray, I don't think. This is a formula that if somebody says, what is substitution, and you told them this, they'd say, yeah, you know what you're doing. You understand stuff. So here's the formula. This is all I'm going to do is write this on the left-hand side. It's the integral from g of a to g of b, f prime of g dg is equal to the integral from a to b of f prime of g of x, g prime of x dx. This is the substitution formula. And now let me show you, what questions do you have about this substitution formula? I'm doing this a little bit different. By the way, did you guys all get an email about a substitution like workshop? Yeah, every single one of you should go to that. I know you don't want to, okay? But I think you do want to do well in the next exam, right? And so if you want to do well in the next exam, this would surely help. Lots of people are putting lots of work in to help you guys do better. And you should take advantage of it. That's what I would do. And if something doesn't work out, hey, it might be a total bust. And if it's not good, you come back and you say, Bart, I want that hour of my life back. And I'm like, can't give it back. Okay, but I'll try. Example. We have to give examples. Without examples, you don't understand what's going on. So here's my substitution formula. Fantastic. Bart, give the people an example. Okay. Integral from 1 to 5 of sine of 3x to the 5th. Put an x to the 4th out here. dx. Right, that's what we're integrating. Integral from 1 to 5, x to the 4th, sine 3x to the 5th dx. This is our prototypical example. This is the example that you can't miss. This can't be the hard example. This is the yeah, she's yawning, the yawning example. That's right. So this is the boring example right here. So here we go. Let's see how to do this. So you might know another way to do this, but just pay attention here. We'll reconcile everything, maybe, if I'm lucky. Okay, so let's see what we do here. Now, I'm thinking about this formula. Do you see a composition of functions here? Do you see a composition of functions here? Yeah, what do you see? Yeah, where's the composition though? Sine of 3x, right? So you have to look for, let's put little eyeballs in here. There we go. Look for a composition. The reason that U substitution, sorry, it's sometimes called U substitution. I should just call it substituting. You see, the reason that substitution is not magic is that you have to have some skill in finding the composition. And the only way you have the skill of finding, does anybody know how you acquire the skill of finding the composition? You practice. You pretty much have to have done the problem before. You know what I'm saying? If you've never seen the problem before, you might not be able to figure it out. So that's the trick. So look for a composition. And so we see sine of 3x to the 5th. Now I know there's an x to the 4th out there. But when I think about this, when I'm doing it originally, I just think about these two pieces. Okay? And so what I'm going to do is I'm going to think about this formula. And by the way, this formula, I have primes here. But look, every f has a prime by it, right? Every f does. You guys see there's only one f here and there's only one f, and both have primes beside them. It doesn't really matter. I can take them away because it's the same. It's the same. I've just renamed the function is all I've done. I've said now f is the thing, it's its derivative. Is that okay? Is that acceptable? She says, I don't know. She says, if you say so. Here. I can just call it capital F. And then, that's horrible, but that's okay. There we go, capital F. So whatever. My point is that my f here is sine f of x is equal to sine of x, then g of x is equal to, whoa. I don't know where that came from. 3x to the 5th, right? 3x to the 5th. And what we have here is we have f of g of x. Now, what we're going to do is we're going to try to write down our formula here. So let's do it. So we have the integral, and we're going to start. Most of the problems you do in this chapter, and since we're not doing much more than this chapter in this class, most of the problems you do in this class, you're going to be going this direction with the formula. Meaning we'll hand you something like this, and you want to turn it into something like this. The harder problems, you actually go the other way. But that won't come till Calc 2. These, we're typically going this direction. And look what we have here. So I'll write it with that side first. We have the integral from 1 to 5. And so a is equal to 1, b is equal to 5. And then I have x to the 4th sine, I'll keep on color coding this, sine of 3x to the 5th dx. And then this is going to be equal to, and look, I'm saying that g is equal to 3x to the 5th, right? So what happens to the first thing, if I'm going this direction, I'm going from this way, what happens to my 1? It becomes 3. Oh my God, 5 to the 5th? What was I thinking? 5 to the 5th? 5 cubed is 125. 5 to the, well anyway, so this is going to be 3 times 5 to the 5th. Okay, sorry, I picked bad numbers. Okay, but anyhow, you guys should be okay with this, right? Okay, so now what's on this side? This just says f of g dg. So it looks like my f is equal to sine, but we'll see what happens. Leave some space here, because we're going to adjust. We're not going to, I'm not concerned about getting it right on the first try. Sine of g dg, there we go. It looks good. Now, what is, we should take the derivative of, oh yeah, I'm supposed to multiply by the derivative here, aren't I? Where am I supposed to multiply by the derivative? What is the derivative of this thing, by the way? What's the derivative of, what is g prime? Equals 15x to the 4th. Is that close to this thing right here? How far off are we? A factor or a multiple of 15, right? And we can always pull constants in. So really, I can replace that with g prime of x. And look, we need that in this formula right here, right? We need that g prime. And then I just need to put a 1 over 15 out in front. And then it's equal. And then the idea is that the integral of sine of something, what's the antiderivative of sine? Negative cosine evaluated from 3 from 5 to the third. So this is a way of making integrals simpler. That's the idea. Does anybody have, what questions do you have about this? I'll try to clarify anything that doesn't make sense. She says, what happened to this G prime right here, right? Right. So I'm using this formula, and there's no G prime over here. And remember, we just followed our noses with the chain rule. We were a little bit sneaky, but not too sneaky, really. What other questions do you have? If you have any, yeah. This is the UDU, and I'm going to show you that next. This is why the UDU works, basically. You can put the 1 over 15 wherever you want, because it can move in or outside. Oh, where'd the 1 over 15 go? Yeah, it needs to go there. My bad. Wait. Yep. It should be right here. My bad. Well, it does. Thank you very much. I love having you guys around. You make sure I do everything right. What else? Any questions? Yeah, what's up? What was that? Why did this G right here? It's because it should be, let's make it a G. It doesn't matter. It's the variable it's the placeholder variable. It doesn't have any real meaning. Was that your question too? You had your hand up for a second. Yeah, what's up? Where did I get the 1 over 15? So I saw that, if you look here, I needed an x to the 4th out in front. This was going to give me a 15x to the 4th when I took the derivative of this thing. So I had to get rid of the 15. So 1 over 15 gets rid of it for me. Yeah. No? Let's do another example, all right? Let's do another example. And I'm going to show you another way to do this, one that you're probably more used to. And you're going to say, I like that better, Bart. And I'll say, well, okay, fine, whatever. So another way to write this formula is you write it as, let's see if I can find, it's very common to use U instead of G. That's just very, very, very common. So I'll go ahead and write it up here, and then I'm going to erase it. So remember, the letters don't make any difference. A to B, whatever. U of A, U of B. So there's our basic formula. Erase this. Okay. Now here we're sort of going to appeal to the idea of differentials. Do you guys remember differentials? Where a differential, you have du is equal to u prime of x dx. So what you do is you say, well, u equals, and for the u, you're always looking for the function that's inside, whatever that means. So what function looks like it's inside here? X squared. Now you can't just pick anything. You gotta always have to pick the right thing. All right? Sometimes there's more than one choice, but yeah, here it is, x squared. And then you say, du is equal to, what's the derivative? Write down the differential here. So you take the derivative of x squared, 2x dx, right? All right, so now we rewrite the integral. So this is equal to, this integral up here is going to be equal to cosine of u. What I just write is I just write cosine of u to u. Then I say, is that right? I say, is that correct? When I plug everything back in. And in fact, one way to think about it is you say, well, I have u here, I have cosine of stuff, and then my du needs to equal everything else here. And so maybe since I just have a dx and an x here, I could say, well, that means that du, or 1/2 du, is equal to x dx. And so maybe I should put a 1/2 here. She likes that. All right, that's good. Okay, so then, look, when I substitute everything back in, du equals 2x. Do you guys see that when I substitute back in, what's u equal to? X squared, there it is. Du is equal to 2x dx. The 1/2 and the 2 cancel. And so we get the x up here, right? This du gives us that x. And the dx goes over there. Is it okay? People are nodding their head yes. And then what else do we need? We need to do one more thing. We need to change the limits of integration, right? You have to do that. Well, you don't have to, but you run the risk of getting the problem wrong. So this is going to be 1, and then this is going to be 9 here. Is that okay? What? Where did I get the 9 from? So if we look at this formula here, we're going this direction. We're going from this one to here. And so we were going from 1 to 3. And now we go from 1, or 1 squared, to 3 squared, which is 9. Did I answer your question? Great. All right, so let's go ahead and do this one more way. There's one more way to do this, and maybe this is the way you should do it. I don't know. Yeah, go ahead. Right here? Oh, we can just, at this point, we can just do the integral. Look, we can do the integral at the starting point. At this point, we can just do the integral. It's 1/2 integral from 1 to 9 of cosine of u du. U is just a variable. It's just a placeholder. What's the antiderivative of cosine? Sine. This is equal to sine of u evaluated from 1. This is equal to 1/2 sine of u evaluated from 1 to 9. Right? Yes? The derivative of sine is cosine. So, yeah. What? No, you should really write the next step, which is 1/2 sine of 9 minus 1/2 sine of 1. Okay, there's one more way, and I'm going to do the same example again. It's all right. I want to make sure you guys really thoroughly understand this. And maybe, I mean, I really like just using the formula directly. That's what I like to do. But maybe this is the nicest one to teach to somebody. I'm not sure. Let's see what you guys think. So I want to do the integral from 1 to 3 of x cosine x squared dx. And I'm going to use u substitution. So again, I look for a function that's inside. What's the function that's inside? Right. And here's what I do. Here's where it starts to, well, it starts off the same. So I say u equals x squared du. I take the derivative of this. That's 2x, and I put a dx there. If I want to, I can say du over 2, or 1/2 du is equal to x dx. And now I can see that I have my x's and my dx's there, right? These are the missing pieces. And so now, here's where I'm going to start to go different. Instead of worrying about the limits, I just say, forget the limits. No limits. There's no limits. So I just say, well, look at the antiderivative. The antiderivative of x cosine of x squared dx is equal to the antiderivative of 1/2 cosine of u du. How would you know, by the way? Somebody writes down, somebody comes to you and says, hey, is this right? How would you know if it's right or wrong? You take the derivative, what else could you do? You plug it back in. You know these facts here, and then, oh, this one too. And then you just plug in x squared for u, and wherever you see du, you plug in this business, and you should get that. You have to. If you don't, you did it wrong. Okay? So, I lost my limits. I forgot my limits. No problem. Can I anti-differentiate this? Yes, so I anti-differentiate it. What's this equal to? It's equal to 1/2. Antiderivative of cosine is sine of u plus c, whatever, right? What's u equal to? X squared. So this is equal to 1/2 sine of x squared. And now I just evaluate it 1/2 sine of x squared from 1 to 3. And I don't worry about changing limits of integration. All right? If I was thinking very naively, I would think this is probably the best for you. Because what you do is you forget the limits, you plug it in, you get it all the way down to u, and then you've got to change it back to x using this right here. And then you use your original limits. The only concern, there's a suspicion in my mind that we might be able to cook up a question where if you only knew this very rigidly, you might be in trouble. Okay? But I can't think of one right now, but I believe the possibility exists. So it's good to know all this. What's up? Yeah, you don't, the c, you don't need to worry about the c. Because when you subtract here, the c's will always cancel. All right, so this is the one type of problem. There's one more type of problem that you can see with u substitution. What I'm going to do is I'm going to show you this next harder problem, and then we're just going to kind of work some examples until I become exhausted. All right, and then we'll end class. This is the problem. The one I'm about to show you is one that definitely kind of scares me. I hope you don't see it on an exam, because this one is not. If I do it well, I'm going to make it look easy. It's not. Here it comes. Antiderivative of x cubed square root of maybe we should talk about why this one's so much harder than the last one. So we try to look for a function inside of another function, right? What's a good guess? Yeah, sure. He says you say, hey, u is equal to 1 minus x squared, right? And then what was the next step? We take the derivative of this thing. So du is equal to minus 2x dx, right? The issue's here. What do we do with this? We have this written down, and it's actually really good. It's actually completely correct. This will lead us to an answer eventually. But what do we do? Because if I try to write something like this is a tempting next step. You try to write, what's this? This is equal to, what's this equal to? Oh, no, I'm sorry, let's just plug u back in. I'm asking a very simple question. You're exactly right, but very simple question. The square root of 1 minus x squared times, what's du equal to? Minus 2x dx. Is this equal to that? No. And is it, how far off is it? It's off by a multiple of x squared and a multiple of 2. The negative 2. The multiple of negative 2 isn't a problem. We can always multiply by constants to cancel these things out. The multiple of x squared that we're missing here, this is x cubed, this is only to the x, this is only to the first power. That's a problem. All right? And that's a little bit tricky to fix. So we have to be a bit sneakier on how we fix this. Does anybody know how to fix this? What we should do next? This is a calculus trick. Yeah, we want to do something with this. What we do, this is the trick. What you do is you look at u and you solve for x squared. So let's go ahead. I'm going to solve for x squared here. So x squared is equal to 1 minus u. I did that all in one step. I hope it's right. I'll give you guys a second to think about that. X squared equals 1 minus u. All right. So how far off were we? A factor of minus 2, right? You know what? I can take care of that. I just put a minus 1/2 up here. And now there's a minus 1/2 down here. And now these will cancel, right? The question is, how do I get this x to be at x cubed? What if I put 1 minus u here? What's this thing equal to? What's 1 minus u equal to? That's equal to x squared. There's the x squared that will turn this into an x cubed at the end of the, now I have an x squared here. And yes, now this is equal to the original integral. Which way, let me just double check something. Let me see, which way are we going on our, we're still going this direction. We're not going this direction. So I don't think we're ever going to go this direction in this class. Calc 2 you will, with something called trig substitution. Which brings everything you love in math. Trig, integrals, one, big mess, draw a triangle. Fantastic. Okay, so let's see. We got this. Okay, so you might not think, so what we're going to try to do is we're not going to do this integral. We're going to do this one. And you might think, well, Bart, this one looks as hard as the other one. It's not. It's not at all as hard. I'm not terrible at guessing the antiderivatives to integrals. But that one there, I would just kick you out of my office if you ask me. So now, here we go. What's this? This is equal to minus 1/2. What happens? I can distribute this, right? I can distribute here. So it's going to be a square root of u minus u times the square root of u du. And what can we do now? What can we do now to make our life a little easier? What? We could split the integral. Sure, why not? This is equal to minus 1/2 integral of, what should I do with that square root though? What? As to the 1/2, right? U to the 1/2 du minus 1/2 integral of, what's this going to be? U to the 3/2 du. And you can do this, right? You know how to anti-differentiate u to any real number, except for maybe, I don't know, well, positive, whatever, it doesn't, I don't know about 0. Anyhow, let's keep on going. Let's not worry about those pathologies. What's the antiderivative of u to the 1/2? It's either negative 1/2 or 1.5, right? Which one is it? When you take a derivative, what happens to the exponent? It subtracts when you take the derivative, so this one should go up, right? So this is going to be minus 1/2 times u to the 3/2. Put a 2/3 out there, right? Yep. Minus 1/2. Oh, what's 3/2 plus 1? 5/2? Minus minus is a plus? Oh, yeah. This is going to be u to the 5/2. But I have to get rid of the 5/2 because it's not there. So let's put the 2/5 plus c, I guess. Ah, it looks terrible, but it's not so bad. What is u equal to? 1 minus x squared. And so now you plug this back in. And so our final answer, I'm going to rewrite the question, just that's always good to do. The integral of x cubed square root of 1 minus x squared dx is equal to minus 1/2 times 2/3 times 1 minus x squared to the 3/2 plus 1/2 2/5 1 minus x squared to the 5/2, oh my god, plus c. So tonight, what you do, after class, you practice this a couple times, and then you go and you find your roommate or your friend, or you call up somebody at another school who's taking calculus, and you challenge them to do this integral. And then you wow them. Right? Yeah? Yeah, what's up? Well, let's see. 2/3 and 2/5 here, right? So I'm anti-differentiating this thing right here, right? And so if I have u to the 1/2 here, right, du, it's going to equal something like u to the 3/2, right? Do you agree with me here? I don't know. I don't know what's going on. I'm looking for the thing whose derivative is this. And when I take this derivative here, I subtract 1 and pull it down, right? But do you see a 3/2 in front of this? No. So there had to have been a 2/3, so that when you take the derivative, they cancel and you get 1. Yeah. Undoing derivatives is much harder, right, than taking derivatives. And you should always be thinking, if you can get within a constant multiple, you guys know what I mean? Like 4 times, 8/3 times, square root of 2 times your answer, you've got the answer because you can always multiply by something else to cancel that out. All right. What do you guys think about this problem? It's a hard problem, right? Okay. Yeah, this one's super easy, but I guess we should do it still. Okay, you guys ready? Here's an easier problem. And it is sort of a standard one. Compute the antiderivative of x to the 4th, x to the 5th plus 1 to the 99th dx. Does anybody know why we put a 99 in there? That's picked for a reason. If it was a small number, like a square, there's a really easy way to do this. What you do is you just expand everything out. Because integrating polynomials term by term, terms are separated by pluses and minuses, is really easy. You just go through and use the power rule. This makes it impossible for you to expand that out, say, on an exam. So you have to use a substitution rule to do this. This problem is forcing some sort of substitution rule. And so what should u equal? U should equal x to the 5th plus 1. That's what somebody shouted at me. And du is equal to 5x to the 4th dx, right? And sure, I like this. Why not? Look up here. What do we have up here? We have x to the 4th. We have it down here. Let's get this 5 out of there. Let's say, so 1/5 du is equal to x to the 4th dx. Do you guys see that? 1/5 du. And so what's going to happen is we're going to put a 1/5 and a du in our transformed integral. Okay? So let's do it. U substitution used to be a lot more important than it is today because if you look at an older calculus book, like one from the 80s or the 70s, what you'll see is you'll see a table of integrals in the beginning, in the front, and the back. There's like tons. Do we still have that? I don't know. I don't carry my textbook around with me anymore. But just like tons and tons of integrals. And the way you get in the form that they're telling is you use some sort of substitution. That was the idea. Now we have fancy smanchy computers and we don't need to worry about it as much as we used to. Okay, so anyhow, I know this and I know this, so I'm going to say this is equal to the integral of u to the 99. And if I want to get my x to the 4th dx, which are the other two pieces I should have here, I have to put a 1/5 in front of it and a du right there. Can we anti-differentiate this easily? Yes, no problem. This is equal to 1/5 times 1/100 u to the 100 plus c. And what's u equal to? X to the 5th plus 1 equals 1/5 times 1/100 times x to the 5th plus 1 to the 100. Did I make a mistake here? I have the feeling like I made a mistake, but I'm not sure. Does anybody see a mistake that I made, a potential error? Nope, it's good. It's fine. I was just being paranoid. That makes sense? Yep, that's not hard. Yep, not hard. Oh! Okay, this is one of my favorite problems. Let's do this one. Antiderivative of 1/x natural log of x dx. We want to use u substitution somehow. So that means you have to find some inside function and some outside function somehow. Right? What? X ln x, he wants to set u equal to x ln x, okay. And what's du equal to then? Okay, so if we set, by the way, we're just going to try some things. We got to try some things. We're not always going to be right. So let's just try this. What's the derivative of x? It's x times derivative natural log of x. It's 1/x plus 1 times natural log of x. Du is equal to 1 plus natural log of x dx. Does this look good? What do you guys think? That guy kind of shook his head like ever so slightly. Okay, and in no way. This is nodding, not shake. This is shaking. Yeah. So the 1 plus natural log of x, we're gonna have a hard time doing anything with that because somehow this should be say du, by the way. I'm sorry, I'm crazy. But anyway, this is right. This is gonna be hard to use. So we're gonna have to make another guess. What's another? Yeah. Yeah, well, I'm sorry, this is wrong, but sometimes we go down the wrong path. But this guy says here, how about you say u equals natural log of x? Okay, sure. The only way you're going to know if you're right or wrong is by trying it. You have to write something down, write u down, and then write du. You have to try it. And if it doesn't work, it doesn't matter. Maybe you've never done this before, in which case you shouldn't expect it to work. I got beat in chess like 8 times last week or night, mostly by my wife. Okay? That's demoralizing. Anyhow, she doesn't watch these videos. Anyhow, u equals natural log of x. What's du equal to? 1 over x. Now think about it. U times du. Oh, here, sorry. Let's. And then what's our function? If this should be right here, what should it be? 1 over. So look, this looks like the integral of 1 over u du. Is that right? Look at that. He says no. He says yes. Du, sorry, du has the 1 over x here. Plug it in. This is equal to 1 over x dx. This is equal to 1 over natural log of x. The integral sign stays the same. Do you guys see how this works? People are nodding their head yes. If you're shaking your head no on the inside, just raise your hand and I'll try to explain it. You got it now? I'll try to explain. That's all I'll do. I won't care. Yeah, what's up? Ask a question. Yeah, of course. Let me try to do a better job than I did last time. So, I'm just going to explain it one more time. We have the integral of 1 over x natural log of x dx. And I say, hey, set u equal to natural log of x. And now du is equal to 1 over x dx. And so now we're going to write 1 over u du. Check this out. Hang on. 1 over u. Let's put that there. Du. What's du equal to? This is equal to 1 over x dx. What's 1 over u equal to? 1 over natural log of x, right? And then the integral sign's the same. Do you see what's going on here? And this right here is that. And so this is the correct transformation. And my clock is telling me the class is over. No worries, we're going to talk about u substitution on Wednesday too.